Welcome to this session on solid principles in object-oriented programming. Today, we will explore the five essential design principles that make software maintainable, scalable, and extensible. First, let's introduce SOLID. SOLID is an acronym for five design principles that help you write better software. By focusing on making our code cleaner, reusable, and decoupled, we can achieve higher quality and more maintainable systems. Our first principle is a single responsibility principle or SRP. The key idea here is that a class should have only one reason to change. This means that a class should only have one responsibility. For example, imagine a class that handles both customer data and sending notifications. It's better to separate these responsibilities into two different classes. This way, each class is easier to maintain and test. Next is the open or closed principle or OCP. This principle states that classes should be open for extension but closed for modification. In simple terms, you should be able to add new features without changing existing code. For example, instead of modifying a class every time a new feature is needed, we use inheritance and polymorphism to extend functionality while keeping the original code untouched. Moving on to the Liskov substitution principle or LSP, this principle tells us that objects of a superclass should be replaceable with objects of a subclass without affecting the correctness of the program. If a subclass does not behave as expected when substituted for its superclass, it can cause issues. So, we need to ensure that derived classes maintain the expected behavior. Now, let's look at the interface segregation principle or ISP. The idea here is that clients should not be forced to depend on interfaces they do not use. This means we should split large interfaces into smaller, more specific ones. By doing so, we avoid creating unnecessary dependencies and make our system more focused and lightweight. The last of the five principles is the dependency inversion principle or DIP. According to this principle, high-level modules should not be should not depend on low-level modules. Both should depend on abstractions. This promotes loose coupling between components and improves maintainability. In practice, we achieve this by using dependency injection to pass in abstractions instead of concrete implementations. Now that we know the principles, let's look at how to refactor a poorly designed class. For instance, let's consider a user manager class. This class currently handles multiple responsibilities like storing user data, validating it, and sending notifications. We can refactor this class by separating these concerns into different classes. Here's how we can refactor the user manager class to follow solid. We will create separate classes for storing user data, validating user data, and sending emails. We will use interfaces to allow easy extension and dependency injection to reduce tight coupling. By doing this, our code will be more modular, flexible, and easier to maintain. Let's take a look at the refactored code. We now have a user storage class, a user validator class, and an email service class. Each of these classes has a single responsibility. The user manager class uses dependency injection to interact with these services. This is a simple yet effective example of applying solid principles to improve our design. So, what are the key takeaways from today's session? First, remember that SRP helps you separate concerns. OCP encourages you to extend, not modify. LSP ensures that subclasses behave as expected. ISP teaches us to create small, focused interfaces. And finally, DIP promotes loose coupling between components through abstractions. In conclusion, solid principles are essential for building clean, maintainable, and scalable systems. By applying these principles, we can improve our design, reduce bugs, and make our code easier to maintain over time. So, next time you are designing a system, consider these principles to improve the overall quality. That wraps up today's session on solid principles. I hope you found it helpful. Now, I would love to hear your thoughts or answer any questions you might have. Let's open the floor for discussion. Welcome to today's session on design patterns overview. In this session, we will explore the key categories of design patterns: creational, structural, and behavioral, and understand how these patterns can help improve your software design and development practices. So, what exactly are design patterns? Design patterns are reusable solutions to common problems that arise during software development. They provide best practices that have been proven to work in various scenarios, helping us write cleaner, more maintainable code. By using design patterns, we can improve code readability, make our software more flexible, and reduce complexity over time. Design patterns can be categorized into three main types: creational, structural, and behavioral. Each category addresses different aspects of software development. Creational patterns focus on the process of object creation. Structural patterns deal with how objects and classes are organized and related. And behavioral patterns help define how objects interact with each other. Let's take a closer look at these categories. Creational patterns abstract the process of object creation to make it more flexible and dynamic. Structural patterns help in composing objects and classes into larger structures, enabling more efficient organization. Lastly, behavioral patterns focus on communication between objects and the delegation of tasks, helping achieve well-organized object interactions. Let's dive into the first creational pattern, the singleton pattern. The singleton pattern ensures that a class has only one instance and provides global access to it. This is useful when we want to control access to a resource like a database connection, ensuring that there's only one instance of a connection throughout the entire application. Here's a quick look at the code for the singleton pattern. As you can see, the class has a private constructor, preventing instantiation from outside the class. It also contains a static method getInstance, which checks if the instance already exists. If not, it creates one and returns it. This ensures that only one instance of the class is created, regardless of how many times the getInstance method is called. Next, we have the factory pattern. The factory pattern is used to create objects without specifying the exact class of object that will be created. It abstracts the object creation process, which helps in promoting loose coupling. This pattern allows us to create different types of objects depending on specific conditions or parameters without changing the client code that uses the factory. Let's take a look at a simple factory pattern example. Here we defined an abstract button class with a render method. Then we have two concrete classes, Windows button and Mac OS button, that implement the render method differently for their respective platforms. The factory will be responsible for determining which button to create. In the next part of the factory pattern, we define the button factory class. The createButton method in this class takes a string parameter OS type, and based on its value, it creates and returns either a Windows button or a Mac OS button. This demonstrates how the factory pattern helps in deciding which class to instantiate without explicitly specifying it in the client code. Design patterns are incredibly important because they provide a common vocabulary for developers. They help us solve complex design patterns in a more structured and efficient manner. By using design patterns, we adhere to best practices, which leads to more maintainable, scalable, and flexible software in the long run. In our next session, we will dive deeper into specific patterns like singleton and factory, and we will have the opportunity to implement them in real world scenarios. We will also explore more advanced patterns and how to apply them effectively in different situations. Stay tuned for more hands on practice in upcoming sessions. Welcome to day 17 of our course on creational design patterns. Today we will be diving deep into the singleton pattern, a key concept in object oriented design that ensures a class has only one instance. Creational design patterns focus on how objects are created. These patterns abstract the instantiation process, providing flexibility and control over object creation. One of the most well-known creational patterns is a singleton pattern, which ensures that a class has only one instance throughout the application. The singleton pattern guarantees that a class has only one instance and provides a global access point to that instance. This pattern is especially useful when you want to manage shared resources across your application, like a database connection or configuration settings. Consider using the singleton pattern when you need global access to a single instance of a class. It's perfect for managing shared resources such as logging and database connection, where you want to ensure only one instance exists across the application. There are three key characteristics of the singleton pattern: private constructor, static instance, global access point. In private constructor, the constructor is private to prevent direct instantiation from outside the class. Static instance: a static variable holds the instance of the class. ensuring that only one instance exists. Global access point. A public method, typically get instance, provides access to the instance, ensuring that it's used consistently throughout the application. Here's a simple implementation of the singleton pattern in C++. The class has a private constructor and a static instance variable. The getInstance method ensures that the instance is created only once and returns the single instance when needed. In the client code, we can see how the singleton instance is accessed. Even if we call getInstance multiple times, both S1 and S2 will point to the same instance of the singleton class, providing that only one instance exists. The singleton pattern has several advantages. Control over object creation. It ensures only one object is created. Global access. The instance is accessible globally, making it easy to share across different parts of the application. Memory efficiency. Only one instance is created, reducing memory usage compared to multiple instances of the same class. Other advantages include centralized object management. The the management of the object is centralized, making it easier to maintain and manage. Flexible in initialization. The instance can be lazily initialized, meaning it will only be created when needed. Consistency. Consistency ensures that the state of the object is consistent across the application as only one instance is used. While the singleton pattern has many benefits, it also comes with disadvantages. Global state, hard to extend, and concurrency issues are the disadvantages. Global state introduces global state which can lead to difficulties in testing and debugging. Hard to extend singleton classes are often difficult to subclass or extend. Consistency issues arises in multi-threaded environment. Creating the instance creating the instance could lead to race conditions if not handled properly. In multi-threaded environments, the singleton pattern can lead to issues where multiple threads try to create the instance simultaneously. To solve this, we synchronize the getInstance method using locks or mutexes, ensuring that only one thread can create the instance at a time. Real-world use cases for the singleton pattern include logger class, database connection, configuration settings. Logger class ensures a single instance for logging across the application. Database connection manages a shared database connection. Configuration settings is used for storing and managing global configuration settings in one place. Now it's your turn. Try implementing a singleton pattern for a thread pool class. The goal is to ensure only one instance of the thread pool is created and shared across your application. Make sure to handle thread safety as well. To summarize the key takeaways, the singleton pattern ensures that only one instance of a class is created. It provides a global access point to that instance. It's ideal for managing shared resources like logging, database connections, and configuration settings. Be aware of potential issues such as global state and concurrency problems. What's next? We can you can explore other creational design patterns like the factory method and abstract factory. Try implementing the singleton pattern in your own applications and practice identifying situations where this pattern can be applied. Welcome to this presentation on creational design patterns, specifically focusing on the factory pattern. In this session, we will explore the factory pattern and understand its role in object-oriented design. By the end, you will know how to apply it in your own projects. Let's begin with an introduction to the factory pattern. This pattern is a creational design pattern used to abstract the process of creating objects. Instead of directly instantiating objects, we delegate the creation to a factory class, which decides which specific class to instantiate. This allows flexibility and decouples the client code from the class being created. The factory pattern is especially useful when we need to create objects without knowing the exact type, or when the object creation process is complex. It centralizes the logic of object creation, making the code easier to maintain and modify. It's also ideal when you want to keep your client code decoupled from specific classes, enhancing the flexibility of your system. There are three main types of factory patterns. The simple factory pattern, where a single function handles object creation. The factory method, where an abstract method is defined for creating objects and concrete subclasses implement this method. The abstract factory, which provides a family of related methods for creating families of objects. Now let's look at some key benefits of using the factory pattern. First, it helps with decoupling. By abstracting the object creation logic into a factory, the client code no longer needs to know how objects are instantiated. Second, it offers flexibility as the factory can decide which type of object to create at runtime based on conditions or configurations. Continuing with the benefits, the factory pattern also provides centralization of object creation. This makes maintenance easier since changes to object creation only need to be made in one place. Lastly, it promotes extensibility. Adding new object types to your system is easier because you only need to extend the factory without altering the client code. Let's look at an example of how the factory pattern works in practice. Imagine we need to create buttons for different platforms such as Windows and Mac OS. First, we define a button interface that will be implemented by different button types for each platforms like Windows button and Mac OS button. Next, we create concrete classes for each platform's button. For example, a Windows button class would implement the render method to display a Windows specific button, and a Mac OS button would do the same for Mac OS. Now we create the factory button. This factory decides which button to instantiate based on the operating system type. In this case, the factory will create a Windows button if the OS is Windows and a Mac OS button if the OS is Mac OS. Finally, in the client code, we can call the button factory to create the correct button type based on the operating system. This way, the client code does not need to know about the specific classes of the buttons. It simply requests the button it needs and the factory handles the rest. To summarize, the factory pattern is a powerful tool in object-oriented design. It abstracts the object creation process, decouples client code from specific classes, and makes your system more flexible, maintainable, and extensible. It's especially useful in scenarios where the object creation logic is complex or subject to change. Consider using the factory pattern when you need to create different types of objects dynamically without knowing the exact class beforehand. It's also beneficial when object creation is complex or conditional, or when you need to create creation centralize creation logic. This pattern ensures that your client code remains decoupled from specific implementation classes. To wrap up, here's an exercise for you. Try implementing a button factory that can create a Windows button, Mac OS button, and a Linux button based on the operating system type. This will give you hands-on experience with the factory pattern and deepen your understanding of its real-world applications. Thank you for your time. I hope this presentation has helped you understand the factory pattern and how it can be used to improve the flexibility and maintainability of your object-oriented systems. Happy coding! Welcome to day 18 of our course on design patterns. In today's session, we will cover two essential structural design patterns, the adapter pattern and the composite pattern. Let's get started. Structural design patterns focus on how classes and objects can be combined to form larger, more complex structures. These patterns aim to simplify relationships between components and ensure that systems are flexible and scalable. Today, we will focus on two such patterns, adapter and composite. The adapter pattern allows objects with incompatible interfaces to work together. Essentially, it acts as a bridge, converting one interface into another that the client expects. This pattern is typically used when integrating legacy systems or third-party libraries that don't match the expected interface. Imagine you are integrating an old payment system into a modern e-commerce platform. The old system uses a different interface than the one expected by the platform. By using the adapter pattern, you can convert the old system's interface into the one expected by the new system, making integration seamless. Here we define the adaptee, which is the old payment system. This system has its own way of making payments, but it does not match the expected interface of the modern platform. Our goal is to adapt this interface to fit the new system. Now we define the target interface, which is what the client expects. This interface contains the method that the new system will use to process payments. Our adapter will make sure that The old system conforms to this interface. This is where the adapter comes in. The payment adapter class takes the old payment system and adapts it to the expected interface. By implementing the target interface, the adapter allows the old system to work seamlessly within the new system. The key components of the adapter pattern are the adaptee, which is the old system, the target, which is the expected interface, and the adapter, which converts the adaptee's interface to match the target. This pattern helps integrate legacy systems without altering their internal code. For the exercise, you will implement an adapter for an old payment gateway. This will give you hands-on experience in adapting legacy systems to a new unified interface. The composite pattern allows us to treat individual objects and compositions of objects in a uniform way. It's especially useful when dealing with tree-like structures, where both single objects and groups of objects need to be treated the same way. Think about a file system where directories contain both files and other directories. The composite pattern allows us to treat both individual files and entire directories as components, simplifying the management of this hierarchical structure. Here we define the component class, which is the base class for both individual objects like files and composites like directories. The component class defines a common interface for all objects in the tree structure. In this step, we define the leaf classes such as circle and square. These are the individual objects that we want to treat uniformly. Each leaf class implements the common interface defined in the component class, allowing them to be treated the same as composite objects. Next, we create the composite class, graphic group. This class is capable of holding multiple graphic objects, including both individual leaf objects and other composite objects. By implementing the same interface, the composite class can treat all of its components uniformly. The main concepts of the composite pattern are the component class, which defines the common interface, the leaf class, which represents individual objects, and the composite class, which groups objects together. This pattern allows us to manage complex hierarchical structures easily. The composite pattern provides several advantages. It allows flexibility as new objects can be added without altering the existing structure. It also simplifies the handling of hierarchical structures, making the code easier to maintain and extend. In this exercise, we will create a composite structure for a menu system. This system will allow both individual menu items and nested menus to be treated as components, demonstrating how the composite pattern can be applied in a real-world scenario. Let's compare the adapter and composite patterns. While the adapter pattern is focused on converting interfaces to integrate incompatible systems, the composite pattern simplifies the management of hierarchical structures by creating both individual and composite objects uniformly. To summarize, the adapter pattern helps integrate incompatible interfaces without changing the underlying code. while the composite pattern makes it easier to work with hierarchical structures by treating individual and composite objects uniformly. Be sure to practice these patterns to master their implementation in your projects. That brings us to the end of the presentation. Do you have any questions or would you like to discuss any of the concepts covered today? Feel free to ask about the adapter or composite patterns or share any challenges you encountered in the exercises. Welcome to the presentation on behavioral design patterns, focusing on the observer and strategy patterns. Let's dive into these crucial design patterns and explore how they help improve object interaction and flexibility in software design. Behavioral design patterns are all about how objects interact and communicate with each other. These patterns define the way objects should collaborate and share responsibilities, ensuring effective communication and interaction within the system. There are several behavioral patterns, with the observer and the strategy patterns being key examples. The observer pattern helps notify multiple objects when a change occurs, while the strategy pattern allows for selecting a specific algorithm at runtime. These patterns aim to simplify object interaction, ensuring better scalability and maintainability. The observer pattern is a design pattern where an object called the subject notifies its dependent objects known as observers whenever its state changes. Think of it like a news agency that notifies all its subscribers about breaking news events. This pattern is commonly used in notification and event handling systems. In the observer pattern, there are several key components. The subject, which maintains a list of observers and notifies them of any state changes. The observer, which defines an interface for receiving updates. The concrete subject, which implements the subject interface and sends updates. The concrete observer, which implements the observer interface and reacts to the updates. The workflow of the observer pattern involves three key steps: attach, update, react. Attach observes register themselves with the subject. Update, the subject changes its state and notifies all registered observers. React, observers receive the updates and perform necessary actions based on the new information. Here's a simple example. Consider a notification system where users subscribe to receive updates on stock prices or news events. When an event such as a price change occurs, all subscribers are automatically notified. This is the essence of the observer pattern. The strategy pattern defines a family of algorithms, encapsulates each one, and makes them interchangeable. This pattern allows the algorithm to be selected at runtime based on the specific context. For example, in a payment system, a user can choose between different payment methods such as credit card, PayPal, or cryptocurrency. The strategy pattern consists of three main components: the strategy interface, which defines a family of algorithms; the concrete strategy, which implements a specific algorithm; the context, which maintains a reference to a strategy object and calls the algorithm defined by the strategy. The workflow of the strategy pattern involves three main steps. Set strategy. The context sets a specific strategy for its operation. Execute. The context delegates the execution of the strategy to the selected algorithm. Switch. The strategy can be dynamically switched based on the context, allowing flexibility in the system's behavior. Let's look at a real-world example, a payment system where users can choose from multiple payment methods such as credit card, PayPal, or cryptocurrency. At runtime, the user selects a strategy and the system processes the payment accordingly. This dynamic selection of strategies is the essence of the strategy pattern. In this exercise, our goal is to implement an observer pattern for a notification system. The task is to create a system where users can subscribe to notifications and receive updates whenever there's a change in the system state, such as an event or status update. Let's take a look at the code implementation of the observer pattern. First, we define the observer interface, which includes an update method that will be called when the subject's state changes. Similarly, we define the subject interface, which includes methods for adding, removing, and notifying observers. In the next part of the implementation, we define the concrete subject class, which implements the subject interface. The notification system class maintains a list of observers and notifies them when the state changes. It also includes a set message method to trigger the notifications. Now let's look at the concrete observer class. The user class implements the observer interface and reacts to the updates by printing a message when it receives a notification. In this case, the update method displays the received message on the console. Finally, in the main function, we test the notification system. Users Alice and Bob subscribe to notifications and receive a message when the system state changes. We also demonstrate how an observer can be removed from the system so it no longer receives updates. In conclusion, the observer pattern helps decouple the subject and observers, making it easy to add or remove observers dynamically. The strategy pattern, on the other hand, promotes flexibility by allowing algorithms to be switched at runtime, reducing conditional logic and encapsulating behavior in separate strategies. Thank you for your attention. I now open the floor for any questions you might have about the observer and strategy patterns or any related topics discussed today. Hello and welcome to this presentation on UML diagrams. In this session, we will dive into the concepts of class and sequence diagrams, two essential tools in the unified modeling language used for system design. Let's get started. UML or Unified Modeling Language is a standardized way to visually represent the design of a system. It helps developers, designers, and business analysts communicate more effectively by providing a common visual language. UML covers several types of diagrams including class diagrams, sequence diagrams, use case diagrams, and activity diagrams, each serving a unique purpose in system modeling. Class diagrams are used to represent the static structure of a system. They illustrate the system's classes, their attributes, methods, and the relationships between them. A class diagram serves as a blueprint for objects, showing how they interact and are related within the system. Let's break down the key components of a class diagram. Class diagrams contain several types of relationships. First, we have generalization or inheritance, which is represented by a line with a triangle pointing to the parent class. For example, a manager is a type of employee. Next, there's dependency, which is a dashed line showing that one class depends on another. Finally, multiplicity, which describes how many instances of one class are associated with another, like how one customer can place multiple orders. Let's look at an example of a class diagram in the context of an e-commerce system. Here we have several classes: a customer, a product, an order, and a payment. Each class has attributes like the customer's name or the product's price, and methods such as an order or processing a payment. These classes interact with each other to complete the e-commerce workflow. In our e-commerce system, there are key relationships between these classes. A customer can place many orders, forming a one-to-many relationship. An order can have many products, which is a many-to-one relationship. And each order has a corresponding payment, forming a one-to-one relationship. These relationships are fundamental to the operation of an e-commerce platform. Moving on to sequence diagrams, while class diagrams represent static structures, sequence diagrams focus on dynamic interactions between objects over time. They show how objects communicate with each other through a series of messages or events. Let's take a closer look at the components of a sequence diagram. Here's an example of a sequence diagram for an e-commerce order process. First, the customer requests to view products. The system responds by sending the available products. Then the customer selects a product and places it in the cart. Afterward, the system processes the order and the customer proceeds to payment. The payment service processes the payment, and finally, the system updates the order status. This this diagram shows the flow of messages between the entities involved. Now let's practice creating UML diagrams. Imagine you are designing a library system. We have several classes: a book, a member, a librarian, and a library. Each class has its own attributes and methods, such as a member's ability to borrow books or a librarian's role in adding and removing books. Your task is to draw the UML diagram for this system. In the library system, a member can borrow multiple books, forming a one-to-many relationship. The librarian manages both the books and the members, ensuring smooth operations. The library itself contains many books and members, showing how the system is organized. Let's visualize the borrowing process in a library system with a sequence diagram. First, the member searches for a book. The library checks if the book is available. If it is available, the member borrows the book. The librarian records the transaction and the member receives the book. This diagram shows the sequence of interactions that occur when a member borrows a book. To summarize, UML diagrams are essential tools for visualizing the structure and behavior of a system. Class diagrams provide a static view showing classes and their relationships, while sequence diagrams focus on the dynamic interactions over time. We have also looked at a practical example and an exercise to help solidify these concepts. That concludes the presentation. If you have any questions or would like to discuss any of the concepts further, feel free to ask. I would be happy to clarify anything you need. Hello everyone and welcome to today's session on design patterns and principles. Today we will be solving problems using design patterns and our focus will be on designing a notification system. Let's dive into the practical aspects of how design patterns can be applied to real-world challenges. In this video, I will be guiding you through the process. Before we jump into the system design, let's first look at the objectives of today. The goal is to reinforce our understanding of design patterns and principles through hands-on practice. We will solve problems involving common patterns like singleton, observer, and factory. In addition, we will review the solid principles and apply them while designing a real-world system, our notification system. Let's now move to our problem scenario. Designing a notification system. The system needs to send messages through multiple channels like email and SMS. It must be flexible, scalable, and extensible, ensuring we can easily add new channels in the future. For example, if we want to add push notifications or WhatsApp, we should be able to integrate them without much hassle. The system should also handle large-scale notifications and future notification types like urgent or promotional messages. As we approach the design, we need to consider a few key factors. First, flexibility is crucial. New notification channels should be easy to add without changing existing code. Second, scalability. Our design must support handling a large number of notifications. And third, extensibility. We should be able to add new types of notifications in the future without disrupting the system. Now let's discuss the key design patterns we will use to build our system. The strategy pattern will allow us to choose different notification channels dynamically. The observer pattern is useful when we need to notify multiple users about events. The factory pattern will help us create instances of different notification channels based on user preferences. And finally, the singleton pattern will ensure that we have a single shared resource for global configurations like API keys or logging. Let's start with the strategy pattern. This pattern allows you to define a family of algorithms, in our case, notification channels. The benefit of the strategy pattern is that it enables dynamic switching between different notification channels like email, SMS, or push notification during runtime without altering the core logic of the system. Next, we have the observer pattern. In this pattern, we use it when our system needs to notify many users about specific events, such as sending updates. The observer pattern ensures that when one object or subject changes its state, all dependent objects are notified and updated automatically. Moving on to the factory pattern, which is useful for creating objects without specifying the exact class of object to be created. For our notification system, the factory pattern will decide which notification channel to create, like email or SMS, based on input from the user or system configuration. Now let's discuss the singleton pattern. This pattern ensures that a class has only one instance and provides a global point of access to it. For our system, we can use singleton to control shared resources like the configuration of the system or access to a logging services. Now let's begin designing the notification system. The central component is the notification object, which holds the message and the type of notification. We will create a notification channel interface, which will be implemented by concrete classes like email channel and SMS channel. The notifier class will handle sending notifications to the chosen channel. Step 1 is to create the notification channel interface. This interface defines the method send notification, which will be used by concrete notification channels like email or SMS. By using an interface, we ensure that we can easily add more channels in the future without changing the code logic. In step 2, we implement the concrete channel classes. For instance, the email channel class will implement the send notification method to send an email, and similarly the SMS channel class will handle sending text messages. Each class will have its own implementation of the send notification method. Next, we create the notifier class. This class is responsible for sending the notification. It holds a reference to a notification channel and calls the send notification method on it. The notifier class allows us to switch between different notification channels without modifying the core notification logic. In step 4, we implement the factory pattern. The notification factory class will create instances of different notification channels based on input. This pattern helps us decouple the logic of creating channels from the rest of the system, allowing us to add new channels easily. Now let's put everything together. In the main function, we first create a channel type like email. We then use the notification factory to create the appropriate channel. Finally, we use the notifier class to send the notification through the selected channel. This approach ensures our system is flexible, scalable, and easy to extend. So, what are the benefits of our system? First, it provides flexibility by allowing us to add new notification channels without changing existing code. Second, it scales well to handle a large number of notifications. And third, it's extensible, allowing us to easily add more notification types or features in the future. To wrap up, here are some additional practice challenges for you. You can modify the system to add features like retrace logging, retries logging, or rate limiting. You can also explore using the decorator pattern to dynamically add features like error handling. And if you are feeling adventurous, try implementing notifications using multi-threading or queues for improved performance. That concludes our session on design patterns and principles applied to the notification system. I hope you find this session useful and learned how to apply design patterns in real-world scenarios. Thank you for your attention.